Greetings everyone, Dr. Shane back with a pre-lab video. I'm going to try to make this one a little bit more, I guess, conversational rather than lecture style. So what lab are we doing here? So we're doing the Colligative Properties lab, where we are determining the molar mass of a small organic compound called urea. So let's go ahead and get started, and I'm going to kind of explain the pre-lab questions as I write them out rather than just listing them all on the right side over there, because I think it'll be easier to do that so I don't have to write out like a paragraph for each of these. So the questions that I write down, I'll complement those with a little verbal explanation. So here we go, and I'll bounce back and forth between procedure and pre-lab questions. Okay, so the bottom line is, by the time you've done this lab, you've probably already done the calculations. You've probably done a calculation already that takes colligative property data and most likely either boiling point elevation, which is what we're doing here, or freezing point depression, and you calculate the molar mass of an unknown solid. That's what we're mimicking here today using experimental data. So I just abbreviated the title of this experiment. What is the molar mass of urea? And well, you can look up the chemical formula for urea. It's actually in your lab notebook, or you can look it up online, and you know what the molar mass is going into it. So the second question I have up here, which I'll come back to, is what is the theoretical molar mass of urea? And the theoretical molar mass would just be from the periodic table, and the formula is in the procedure. This is mine just with notes. Okay, what I want to do is kind of bounce back and forth between the procedure. Well, mainly I'm just going to do the procedure first, and then I'll talk about the math and the theory. So the procedure is pretty clear. I'm just going to kind of walk through it. It tells you to review how to use a pipette, which I'm going to remind you how to do that. We're using a 10 milliliter pipette, so a big one. I don't think we've used one that's been this big before. The procedure says to use a 250 milliliter beaker to set up a water bath using a stirring hot plate and then a bunch of other stuff. So I'm not going to read that whole thing to you, because what I have here is it's already set up. So what you want to do right when you come in the lab is get out a ring stand and a hot plate, and the hot plate you choose may not sit all that securely on the ring stand, so you might not do exactly this setup. You may have the hot plate sitting off to the side. Okay, so you want a 250 milliliter beaker and a water bath. This can just be tap water, by the way. We're not using this as part of the experiment. It's just there as a heating source. So, maybe 2/3 full, so that when you put the test tube in there, it doesn't overflow. But that wouldn't be a disaster if it did. And then you want to heat it. I'm just going to kind of mimic this. Make sure you use the heat feature, not the stir feature. You can put a stir bar in here. That'll heat it more efficiently if you want to, but you really don't need to. You don't really have to crank up the temperature on this, because you do not want to boil this water. Well, first off, why? This is actually a post-lab question. We're going to take ethanol, which has a boiling point of, 78.50 degrees Celsius, pure ethanol. And we don't want to boil the ethanol. We just want to heat it. So if we take that back. Of course we want to boil the ethanol, because we have to measure the boiling point with solute and without solute. But what we don't want to do is to lose too much of the volume that we put in here. That's actually a source of error. It's almost impossible to do that. Okay, so yes, we want to boil the ethanol, and yes, we want to boil the ethanol with the urea dissolved in it, because this lab is boiling point elevation. Okay, so that's what you want to do. So get this lower portion of the apparatus set up. Then it says to get a large test tube and a thermometer stopper condenser apparatus. These will be out ready for you to go. There's a thermometer. There's this is so that the pressure doesn't build up and blow that off. And that should sit in there pretty snugly. There shouldn't be any cracks. Check the stopper, make sure it's good. Its integrity is good, and then it sits in the test tube rather snugly. That should be fine. You also don't want the thermometer touching the sides of the test tube or the bottom of the test tube. Remember, when you measure the temperature of a liquid, whether it's a pure solvent or a solution is irrelevant, you want the bulb of the thermometer to be suspended in the liquid. Okay, not touching the sides and not touching the bottom. Also, I think you're going to need another thermometer to check the temperature of the water. Again, you can plug it in. It's actually not a very safe thing to do because you can knock it over in this whole apparatus. But this is what you would do, just kind of suspend it in there to check the temperature of your water. Make sure it gets to around 90 degrees. If you don't get 90.0, that's fine. Keep in mind, all we want to do is use this as enough to heat it so that the ethanol in the interior boils. And there's, what is that, like a 21.5 degree difference. Actually a little less because we're above sea level, but we're not going to get into that too much. All right, so before I get started, we are going to use ethanol in here. So we're not using water in here. I see students sometimes, they go through the calculations and they end up using water, okay? And I just remembered something I want to check to make sure that you can see the chalkboard. Sorry, a little sloppy today. Yep, okay, I wasn't sure I had that focused out enough. All right, so you get this apparatus set up, and let's review how to pipette. So you want to pipette 10 milliliters of ethanol into this test tube, and it's important that all of it go into the bottom. If you have drops on the side, well, that's a source of error, because then not all of it is undergoing the boiling part. All right, so I'm going to put on some goggles here. And also keep in mind, volumetric glassware, most of the time we're talking about volumetric flasks, have 2 decimal place precision. And I'm pretty sure, your instructor may correct me on this, but I'm pretty sure these, it's not 10 milliliters, because that would be 1 sig fig if you just use 10. That'd be kind of dumb. Even if you put a decimal place after the 0, it'd be 2 sig figs. You can get 4 sig figs on these. And this is the volume of ethanol. An abbreviation for ethanol used in science, organic chemistry in particular, is ETOH. So this is ethanol. And this is the big bottle of ethanol we had in the stockroom. I'm just going to show you that. It says 200 proof. If you've ever heard of proof is often used in alcoholic beverages. So like if something's 100 proof, it's 50% ethanol. So this is 200 proof. It's 100% ethanol. It has some other stuff mixed in with it so people won't consume it. That would be seriously dangerous regardless. So a couple things. You're certainly not going to be given this large container at your individual station. That would be too much volume. That would be dangerous. You'll be given a smaller container. I don't know exactly what we're going to do yet because I'm making this video way ahead of time. But the point is this. You don't pipette directly from the container that you're given. That would be the primary container. So say we have a little brown bottle that's, we've used these before, like little ones about this big, or maybe it's one that's medium sized like we've used throughout the semester. You would never take your pipette, take the cap off and plunk it in there. First off, that's dangerous and that contaminates the solution. You always pipette, with very few exceptions, from a secondary container. So I just poured carefully some of this ethanol into a small beaker. Only need 10 mils, so don't waste it. And I actually probably added too much here. I added, well, the beaker's terrible, but I put about 25 mils in there, so that's being a little wasteful on my part. Okay, pipetting. So you have the pipette, and your instructor, again, may have slight differences here. You want the pipette bulb. Check the pipette bulb to make sure there isn't any liquid up in the bulb that you are unaware of because you can't see it. You can always come over to the sink and if it sprays a bunch of liquid out, then you want to take it apart, clean it, dry it, or just get another one. Also make sure your pipette bulb doesn't have any cracks in it because it won't draw liquid up or it won't create that pressure differential. And I have a bad example here. This is one that was in the demo drawer up here, so we're going to throw that one away because that is not going to work. So pipetting, the basic procedure is you depress the bulb, you put your pipette in gently, don't jam it on the bottom of the container because that will make it very difficult to draw liquid up. Set the bulb gently on top and draw liquid. Oh, there must be a crack in this one. Okay. I'm just going to have to mimic this then. That's okay. Yep, there's a crack in this. Well, I should have checked this ahead of time. You think I would have done that? Okay, so that I'm giving you a bad example of what to do. I'm going to go get another pipette bulb so that I can actually do this experiment. This looks like a brand new one. So this is what's going to happen in lab. Your pipette might have a crack and you can't even tell. So again, press the bulb. Gently. There, that's much better. I don't know what you can see on the camera. And then you want to draw it up slowly. Don't let it shoot up when it gets into the smaller part. Past that etched line, the brown line in this case, so come up past, I'm just passing it a little bit, and then take the bulb off and put your finger over the top of it. I didn't do a very good job there. It's okay. I don't know if you can see it. The meniscus of the ethanol is way up here. The etched line is down here. You want the bottom of the meniscus, just like a graduated cylinder, the bottom of the meniscus to be right on that brown line. And you know, you don't have to sit here and watch me do this. So you just kind of let the, maybe I won't do it perfectly, which is okay. You move your finger, let a little air in so that the atmospheric pressure pushes it back down. And you can do that slowly. Sometimes students are better at this than I am. There we go, it's going down, it's going down. And for the purposes here, no, that's actually pretty good. Yeah, so the meniscus is, I did that perfectly. That's rare that I do that on the first time. All right, so then you want to transfer this. And if you look carefully on the side of this, it says TD, which means to deliver. A graduated cylinder is TC, to contain. So then, put that in your test tube, let it drain, and just let gravity do its thing. If you have a drop sitting on the end, touch it against the side of the glass. It will use actually intermolecular forces between the glass and let it draw that last bit out. And we probably talked about this last semester. You'll notice there's a very little bit of ethanol left here. Leave it in there. This is meant for 10.00 mils to come out the bottom, not to contain. So you don't like blow that out with your mouth, which sounds dumb, but you wouldn't take this and expel the remainder. Good. So you've got 10 milliliters of ethanol in there, and it looks like I transferred it pretty well. I don't have any on the side. And okay. Now I think we're getting ready to go. So you use your clamp, and you may want to use your bigger clamp that might hold it more securely. So you want your ethanol, I think it says to be below, yeah, okay, that should work. I think, yeah, all the ethanol, it's in the water bath. The test tube is not touching the bottom. It's not touching the sides. It's suspended. Then the thermometer, and you probably want to make sure you have the thermometer turned towards you so you can read it. So again, you want to have this heating up. I'm just going to turn this off because I'm just demonstrating it. So then you put, and I may be doing this out of order from the procedure. It's okay. Then you want to have the bulb of the thermometer. In this case, it looks pretty good. The bulb of the thermometer is almost entirely down there. I do not want you trying to adjust the thermometer or the condensing tube. I don't want you doing that because they can snap. Okay, that's really kind of dangerous. So, if anything, just go get a new apparatus. Like if the thermometer's up too high or something, or we'll help you. So that looks pretty good. It's not touching anything. What does it say? Check that the bulb extends below. Ask your okay. Use a ring stand and clamp it. Okay. Carefully. Oh, I forgot to do the capillary tube, didn't I? Obtain, I'm going back in the procedure. Obtain a melting point and drop the open end down into the ethanol. All right, these are capillary tubes. We used these last semester to measure melting points. We had a solid, remember if you're here, you tap it and you get some solid in there and tap it and you measure the melting point using the device. So it's the same tube, but we're using it for a different purpose. So it's got the closed end and it's got the open end. So you want it to go open end down. You want to kind of plop it in there. Sometimes students have found tweezers are a little bit easier to manipulate. These are also known as forceps. But you could probably drop it in there. Sometimes these get stuck to the side of the test tube on the way down. You just want to make sure it's sitting in the bottom. But you also want to make sure that it's not so straight up and down that it's sticking on the bottom of the test tube. That can be a little tricky, but we'll talk about that in lab. And then carefully, because the capillary tube is kind of tall, you don't want to break it when you put your thermometer apparatus back in, because the capillary tube is about that high, so it has to kind of go next to the thermometer. So I think we're good. Obtain a melting point, drop its open end down into the ethanol, insert the temperature condenser apparatus T/C. Okay, use the ring. Okay, so I did this a little out of order. Okay, good. So here's how you collect data. After you assemble all of that, now it'll probably take you less time than it took me to show you. So you've got the water, it's about 90 degrees. You kind of have to slide this thermometer in there. Well, what are you going to see happen? Well, what's going to happen is, easier to see it, I don't think even drawing a picture is going to help. When you get really close to the boiling point of ethanol, you're going to see a steady stream of bubbles. They're very small bubbles that will come out of the bottom of the capillary tube. Again, I'm waving my hands around, but you'll see it about. So a steady stream will come out. When a steady stream of bubbles escapes from the open end, so down at the bottom of the test tube, remove, this is key. This is key. When you see that steady stream, then you take the clamp and remove the apparatus. Why do you do that? Okay. Then what you're going to see, you're going to watch very carefully. Watch the capillary tube, and you'll see ethanol go up into the capillary tube. When you see the ethanol level go, so the bubbles are going, right? So there's no ethanol in there. When the bubbles stop, the ethanol will go up into the tube. You record that temperature. This is basically a barometer that you're building. Boiling point is where the atmospheric pressure pushing down is equal to the vapor pressure pushing back. When that happens, that's when the ethanol will go up into the tube. It'll probably be easier to see it than me explaining it. Plus, you know what the boiling point of pure ethanol is supposed to be. The boiling point of pure ethanol is 78.50 degrees Celsius. Which also begs the question, why are we measuring the boiling point of ethanol when we have it? We can just look it up in a book and then have it. Well, that's because thermometers are not perfect. These lab thermometers are definitely not perfect. So we have to make sure that to calculate a delta T, which is what we want to do with the math, a delta T, we use the same thermometer. So we have a boiling point with an imperfect thermometer of ethanol, and then we have a boiling point with an imperfect thermometer with ethanol with urea in it. So that we take away that systematic error in the thermometer. That's a very important experimental point. You wouldn't normally think about that with thermometers as an instrument, but they are. Okay, so I think that's the procedure. Okay. Then it says remove this, and we're only doing one trial of each, I think. By the way, if you have to repeat it, it's really quick. Observations, observations, observations. If you see the ethanol start to boil and it's condensing all over the inside of the test tube and it's not staying in the bottom and you have droplets everywhere, which you'll have some, that's something you want to write down. That's a source of error. It can be. Okay, so then you want to take, it says about 1 gram of urea and dissolve it in there and repeat the procedure. And again, the boiling point's going to go up. That's one of the questions actually. Why does the boiling point go up? And I'll clarify that a little later. Transfer it there. Do not boil the solution. Determine the, okay. So you basically do everything you did before, except you put 1 gram of urea in here. And I'm not going to go through that whole procedure. I just want to show you a couple of things. So this is urea, like a container we would get from the chemical company. I forget, it's a Sigma, and it doesn't matter which company. And we'll have out little containers like we usually do. And it dissolves pretty quickly in ethanol. Again, this is not water. We're not dissolving it in water, we're dissolving it in ethanol. And just gonna, I don't know if this is really gonna help. Just to show you, they're kind of big crystals. Now, it's not really, these crystals here are fairly sticky. Okay, so, you know, you've dealt with this before. So what we're gonna do is, these crystals are like little beads almost. Yeah, they're, well, I can't tilt it because it's gonna make a mess. They almost look like little white ball bearings. Those are actually gonna take a little while to dissolve if you leave them as those spherical particles. So we're gonna take a mortar and pestle. This is the mortar, this is the pestle. So you'll take some of this. You only need a gram. I have no idea how much I put in there. So put some in the mortar and pestle. This is very non-toxic stuff, so it's very safe. I could be wearing gloves, but you don't need to. So I put some urea in here. Now, observations. Look at it. Describe what it looks like. Describe what the ethanol looks like. Ethanol should be a clear, colorless liquid. If you pour it out of your container and it has a yellow tint to it, something's wrong. So urea should be a pure white crystalline solid. Looks good to me, but always write that stuff down, even though your procedure doesn't always tell you to do it. So leave the mortar on the bench, and you push down and turn with the pestle. So you push down and you turn. What you don't do is get all jackhammer on it, or attack it like you're stabbing it. So don't get all stabby. So, all right, so you grind it up. It's like a spice grinder if you do any cooking at home. So now it is a fine powder, which is going to dissolve much more quickly. The next part I think you can handle. So you use your weigh boats. I think you guys are using these little ones. I guess you could use a big one. We'll see. A gram is actually a lot, so we might put out the big ones. We'll see. So you weigh a gram out. I'm not going to weigh a gram. I think you know how to do that. And this is way less than a gram. I'm not even going to show this next part. Then you'll take this off and transfer it. This can get messy. You want to be very careful. You want to get all of this solid into the bottom. If you're kind of careless and you just sort of dump it in there, it's going to get all over the sides. If it does, even if it only gets a little bit, it's hard. Let me just, so if you're careful, you can drop the solid right down the middle of the test tube, and I have a very small amount. If you're careful, have it all fall right down the middle. It doesn't even touch the sides. And then, if you need to, you can do the whole, hold it at the top and tap it. Because it actually swirls the liquid in there. It takes a little bit to dissolve. It will dissolve when you put it in the warm water very, very quickly. If it gets caked all over the side, like I don't know, you had too much coffee or something, you can kind of take the ethanol and make sure it all goes down. Like you don't want any solid on the sides. That would be a source of error. Actually, I may have caused a source of error by getting ethanol all over the sides. Okay. So there are some sources of error here. So the point, I'm not going to show all. The point is, all this urea has to be dissolved. And like I said, it will dissolve even if you need to get a stirring rod and put it in here. It's not typically what we do, but sometimes if the spatula is clean, you can reach it down, almost use like a paddle wheel. I wouldn't recommend this. Just make sure you don't break the capillary. Be careful. We're only doing one trial with each. We'll see. This lab could be a challenge to do in an hour because it's taking me so long. Okay, so assemble the apparatus, wait till the bubbles come out, steady stream, pull it out, measure the boiling point. It should go up, and it's not going to go up by like 30 degrees or anything. I don't remember what it is. It's only a couple of degrees changed. And that's it. Then what you do is, wash everything. We'll have a waste container over there, and that's the experiment. So all the data you're getting is, let's see, you're getting the mass of urea, the boiling point of pure ethanol, which should be about 78.5, and the boiling point of ethanol with about a gram of urea dissolved in it. I think that's all the data you're getting, just all that work for 3 data points. Okay, let's talk about the pre-lab questions. So some things I want you to do. All right, so first off, why does dissolving a solute, and this is important, I'm gonna come back to this, this is a solid solute, it's a non-volatile solute, and urea is also a weak electrolyte. Okay, so I'll end up having you define what does non-volatile mean, and what is a weak electrolyte mean. Okay, but I'll give you some more information on that. So why does the boiling point go up? What physical property, why does the solute change the boiling point of ethanol so that it goes up? Okay. Probably talked about that in lecture. You can actually get your answer. You can calculate the molar mass of urea. It's CH4N2O, right? CH4N2O, you can get the molar, or just Google it, but calculate it. So you know what your answer is. So you have a hypothesis even before you come into the lab. The hypothesis is the theoretical molar mass. All right, and just some questions here. Oftentimes we give you a bunch of dry lab questions. This is no exception. So this one is not a dry lab calculation though. Let's just calculate a molality. So molality is moles solute per kilogram solvent. So let's assume that you've got 10 milliliters of ethanol, so that's your solvent. You've got the density here, right? Yeah, you've got the density. So you can convert that to kilograms, couldn't you? Fine. But the only thing you don't have is you don't have a mass of urea. And in lab, you're obtaining about 1 gram. Now you don't write down 1 gram in your lab notebook. You write something like, 0.9927 grams. And let's put the chemical formula, which you have to pretend you don't know in this lab. So that's just a solution prep calculation. So moles, solute per kilogram, solvent. That's molality, right? Yeah, moles per kilogram. Okay. So that's fine. So do those. The introduction to the lab mentions section 11.4. So read section 11.4. It gives you've probably done exactly these calculations. What really you should do is specifically look at example 11.11. Now that example uses freezing point depression to calculate a molar mass. It's the same basic procedure. Now in that problem, they're not using ethanol, they're using chloroform. So you have to make sure you look up the appropriate data, freezing point data, and a freezing point depression constant, not a boiling point, not for water and not for ethanol, for chloroform. And then, so look at that one as an example. You can redo it if you want to. But do the check your learning problem. So you're given one that is boiling point elevation. Again, I think it's chloroform, it doesn't matter. You just scroll up in the chapter to get the data you need, boiling point and all that good stuff, and the constant, let's look that up. And you're given the answer. So just do that problem, get the answer, and then you really know what you're doing before you come into lab. In fact, if you want to, you don't have to do this. If your instructor has you set up a calculation section, which you always do, you can actually use this example and set up your calculation section ahead of time, so that when you write your lab report, you just kind of follow along. You've already got the recipe written out just for efficiency's sake. This lab is a lot of work at the front end. It's a little bit tricky to get the data. It's pretty quick to write up, so it'll be pretty straightforward. Okay. A couple things I'm going to ask you to do in addition, but I need to kind of go through this here a little bit. So here's the formula. The change in boiling point, you already know this, is equal to I, which is called that Van't Hoff factor. Usually we assume, well, we have to make some assumptions. and this is boiling point. And I'm not going to go through all the math. We're not solving for the new boiling point here. We're going to have a number here. We're actually going to use this equation to calculate molar mass. So, okay. So make sure that you're using, oh, and then what is delta V? So delta V is the boiling point of the solution, so ethanol and urea, minus the boiling point of the solvent, ethyl alcohol, 78.5. Well, use your data. Don't use 78.5. Use whatever data you collected. Equals I times KV. And again, make sure you look that up for ethanol, not water. So that's the boiling point elevation constant for ethanol. You're given 1.22. And I'm not going to go through the math here. Question number 5 on the pre-lab. I'm going to write this here for a second. Urea is this. Oops. Okay. That's the structure of urea, I think so. What's the formula again? CH4N2O. Let's double check that. So 4 hydrogens, an oxygen, 2 nitrogen. Okay, so you can look this up and that's fine. And you know that the structure of ethanol is that. So that's ethanol. So question 5. What are the intermolecular forces when I take urea and dissolve it in ethanol? What are the primary intermolecular forces in between these two molecules? And you can identify there's only a handful of intermolecular forces that you learn about. And you could put your partial positives and negatives, you kind of see where I'm headed, and maybe make a diagram of how urea would interact with ethanol. Okay? And, okay, the other thing I want you, this one may be a little tricky. We assume, I think I can come over here now. We assume that when urea, so I'm just going to use the chemical formula, CH4N2O, so we put it in ethanol, let me just say ETOH, just for, so you put the solvent above the arrow, that it stays together. This is a covalent molecule. So it's not ionic. If this is ionic, it would split up into ions, but it's not ionic. It's covalent, okay? So we assume that when it dissolves, it's still urea. And what do we put as a subscript now? Normally we put AQ for aqueous, but this isn't water. So I guess we would have to put the subscript ETOH. This is sometimes called ethanolic urea. Sometimes called alcoholic, because it could be urea, but that sounds a little weird to call it alcoholic urea. Fine. Okay, so we assume that. This is kind of a, you may have to look this one up. Oh, yeah, so, sorry, I'm kind of rambling here. I just think this is an interesting question. So we assume that I equals 1. And that's called an ideal solution. In this case, it's an ideal solution. If this is an ionic compound that broke up into 2 ions, the Van Hoff factor would be 2 in an ideal solution. But this is not ionic. So, the question I have for you is, how would I be affected if urea forms a dimer? I'm not overly concerned about this as it's a good conceptual question that's often asked on quizzes and tests. Well, first off, what's a dimer? A dimer is when you have so much of the solute in solution that it interacts with itself. What we assume in an ideal solution is that you have urea over here, ethanol over here, but the urea is not interacting with itself. Well, what if I just keep dumping more and more urea in there? That assumption starts to break down. And a dimer is where a molecule of urea interacts with another molecule of urea, and they operate like a unit. So you've got urea, urea. You can actually show the intermolecular forces between two urea molecules. Well, what happens if they don't separate, but they're linked together? That's called a dimer. So 1, 2, dimer. Your book, actually, if you go to your book and type in dimer, they give you an example with acetic acid. You can do that. So how would the Van Hoff factor be affected if urea forms a dimer? And I think that's going to be about it. That's a lot of a video, but that will really kind of clarify things as we get going. All right, we'll see you in lab.